All right, time to look at the different terms of this and put them in a little more familiar territory. Ampere's law has this J. We sort of have an inkling of what that is. J is current density coming from conductivity in a material. Conduction current density. It's conductivity times electric field. If you got a high conductivity material, you're going to pull a high current density through it for the same electric field that wouldn't draw a lot of current density in something like glass. You had copper versus glass. Okay, so it's got some material properties built in. I'm emphasizing this because later on when we're just talking about waves, the main goal of chapter 9, we don't have any materials around. We can even be in a vacuum and we just got these time varying fields and we still have interesting things happening. So this could go away. This piece that we just learned about could be the only thing. Okay. And this other one we're calling displacement current. And technically displacement current density, so all the units match up. Current density. Okay. One more thing that we do in chapter 9 is we put these solutions. Once we start having to take time derivatives of things, we don't know what that thing's going to be, but if we can solve it for a sine wave, those are really easy to take derivatives of. Even easier is a complex exponential. So E is some amplitude, and these are vectors. The j omega t. Okay, so we could describe an electric field as having this little amplitude that's just a function of x, y, and z times sinusoid, complex exponential. And later on we're going to take the real part of it. That's one thing that bugs people about it. Sine omega t plus j sine omega t. We love sticking with this and then leaving this for the last part when we're taking time derivatives, dE, dt. They don't affect this part. E naught, just a function of x, y, and z. I'm not going to keep writing that. I'm going to bring down j omega e to the j omega t. And from now, we're just going to look at magnitudes and amplitudes. We're not really going to worry about this j. We'll see what it does later on. But we can turn this thing into, oh yeah, and d is epsilon e. So when it's in the sinusoidal format, we're calling it time harmonic in this book. Meaning we're just talking about solving it for one frequency component. What frequency component, or we're just going to leave that as a variable and we're going to solve it, and then later on we'll have a solution that we can enter different frequencies into and see what happens, or we can superpose the solution for a bunch of different frequencies and pretty much get any time signal that's useful using like a Fourier series. When it's time harmonic, dd dt becomes epsilon, and this is just the original E. And we're going to put amplitude on it, so we're going to ignore this J. Okay, so we're getting a couple things on this side of the equation, Ampere's law, that are proportional to E. Okay, magnitude of the displacement current density versus the magnitude of the conduction current density is an interesting ratio. So displacement current is the thing you have in a capacitor. Is something that's charging up and maybe it's changing, maybe it's got an AC signal on it. And displacement current density is 0 when you have DC, and as we used to have when we had electrostatics world, displacement current density is going to be sigma E over just the magnitude of this thing, omega epsilon E, and those are going to cancel out. Okay, so whether we've got something that behaves like a metal conductor or more like a capacitor is determined by this conduction to displacement current density ratio. And you can see that that's a function of frequency. Okay, at high frequencies it's all displacement current. And we're going to look at that a little bit more when we pick up with waves. We're going to start saying, well, let's get rid of all the conductive material. Even epsilon is just going to go back to what it is in the vacuum. And we're still going to be able to propagate fields through space because a changing electric field has something to do with a magnetic field.